Hi there, welcome back to lecture 16 of our course Advanced Quantum Mechanics. We studied the position and the momentum eigenbases most recently. Now, let us consider the energy eigenbases. Now, what the energy eigenbases is depends, of course, on the system at hand. It's right here. Energy eigenbases. Well, what the spectrum is depends on the system at hand. And in general, the spectrum of the Hamiltonian, of the system can be, well, discrete. It can be continuous, and of course it can be mixed. What though is the physics of the spectrum being either discrete, continuous, or mixed? It turns out that some very general statements can be made about that. I think I hinted about these things earlier, but now let's look really into this. So consider the case where it's discrete. Case 1, spectrum. Well, actually, let's look at the eigenvalue separately. So a discrete eigenvalue. Discrete eigenvalue. Let's call it En. And it comes with an eigenstate with normalizable eigenstate of the Hamiltonian, and the eigenstate is called En. So we have that H hat En equal to En. And because it is part of the point spectrum, because it is an isolated point in the spectrum, En, we know that the eigenvector is normalizable. So we have that En is equal to 1. Let's see what that means in the position representation. It means that, well, En, which is En identity En, so let's write it 1 equal to, is equal to the integral of En x En dx over the real line. Now, what is this? This is the energy, is the nth energy eigenfunction in the position representation, the nth energy eigenstate in the position representation. Let's call this psi En of x. So this is the position wave function of the nth discrete energy eigenstate yeah, that's what it is. And then, of course, is its complex conjugate over here. So therefore, this is the integral over R of psi star En of x psi En of x dx. So what we now know is this wave function has to be square integrable. And that means that if we plot the modulus of it, so psi En of x, the modulus of that, then it looks something like this. But we also know that it has to go to 0 eventually, and relatively fast, so that the integral can come out to be finite. What this means is that this wave function can be non-zero, can be appreciably, noticeably non-zero, only in some finite region. And in most of space, it has to be almost vanishing or vanishing in order for that integral to be finite. So therefore, we say that the state En is a bound state. You see, this might be the wave function of an electron, for example, which is exposed to the attractive potential by a proton. And so the electron is in some orbit, in some orbital around the proton. It's described as an orbital wave function around the proton. This electron is bound by the proton. The probability for finding the electron close to the proton is high, but the probability diminishes quickly as you go far away from the proton. So the electron is said to be captured by the proton. It is in a bound state. Remember that when a space is infinitely large, such as here the real line, then when we say that the wave function is negligible almost everywhere, then we mean that literally, right? You have that the wave function is non-zero in some finite region, and there is still an infinite amount of other regions where the wave function has to be small. So that's why we call it a bound state. But it doesn't have to be an electron bound to a proton, right? This could be an atom bound to a molecule. Okay, so that's a bound state. Now, the next case, this was case 1. Now let's look at case 2. So we have now E is in the continuous spectrum of the Hamiltonian of our system. Therefore, this state is not normalizable, and therefore the integral over psi E of x star psi E of x, that's the position wave function of a non-normalizable energy eigenstate, well, it's not normalizable. So it's not smaller, it is infinite. Equal infinite. Okay, so what that means is that the wave function now doesn't have to decay. In fact, it shouldn't decay towards infinity. Psi E of x, modulus, and now this could go on forever in each direction. It doesn't have to be bound. So the particle could be it is a particle that is not bound. And these non-bound states are called such energy eigenstates are called scattering states. Example. Let's say free particle. Here we have that the Hamiltonian is just p hat squared over 2m. Now from that, we can tell right away that all momentum eigenvectors are also energy eigenvectors, right? So therefore, all p are also h hat eigenvectors with eigenvalues p squared divided by 2m, with eigenvalues p squared divided 2m. So we have that h hat acting on p is equal to p squared over 2m p. So from that, we have that since the spectrum of the momentum operator is the real line, we have that the spectrum of the Hamiltonian of the free particle, so let's write it explicitly, the spectrum of the operator p hat squared over 2m is equal to the positive numbers only. All right, now what are these momentum eigenstates? Let's look at them in the position representation. I mean, remember, they are energy eigenstates as well. So let's look at them in the position representation in x hat bases. Well, there we have, if you remember from the previous lecture, square root of 2 pi h bar, and then e I x p over h bar. So this is the wave function. It's the position wave function of an energy eigenstate. Yes, it's also a momentum eigenstate, but for a free particle, momentum eigenstates are also energy eigenstates. So this is the position wave function of an energy eigenstate. And look at the modulus of it. The modulus of it is just 1 over square root of 2 pi h bar. So the modulus is constant. This wave function is not localized anywhere. This describes an electron that is not bound to anything. It's also technically not really scattering of anything because it's a free particle. But you can imagine now how this generalizes to arbitrary systems. Namely, and this would be now the generic case, case 3, generic or mixed. So let's say we have a particle whose Hamiltonian is, this is an example. Hamiltonian is p squared over 2m plus some potential v of x hat. Then how does this look like? Well, let's say v is some potential function, v of x, that looks like this, for example. Or, why not? Usually we would write it as more of a dip, something like this. In this case, typically, mixed spectrum. And we now see from the previous considerations why we should expect this. You see, if the particle has a little energy, then it will be trapped in this potential well down here. And if it's trapped, the wave function should decay quickly so that it is square integrable. And that means that the eigenvalues ought to be discrete. that means that in here, where the particle would be trapped, where it therefore has a normalizable spectrum, as normalizable eigenvectors, there, the eigenvalues should be discrete. It should generally look like this. If we just indicate here symbolically how that would look like. These are the energy levels down here in the potential, and then maybe some more here and there. I mean, these are meant to be horizontal lines, right? So these are the, actually I could have just drawn points over here, right? So these are the energy eigenvalues corresponding to eigenvectors that are normalizable, that therefore describe, that have wave functions that are square integrable, that therefore describe particles that are trapped in this potential. But then if a particle has energy that is exceeding the potential, the highest potential, then it should be able to fall into the trap, but come out of it again. I mean, it will just scatter off this, right? So particles that are that have enough kinetic energy cannot be confined in here. They would always climb their way out. So there will be particles. I mean, the particle can have enough energy such that it will have a non-normalizable wave function because it won't be localized. But we know that these come with a continuous spectrum. And that's what we have. We have in general that then there is above some energy level, this line is meant to be where that line is, sorry about it. All of this here, all of these energy levels are going to be part of the continuous spectrum over here. So what we expect generally for potential like that is that there's going to be some discrete eigenvalues here and then a continuous spectrum above. This is generic for potentials that look like that. That we have a discrete spectrum at the bottom and then we have a continuous spectrum on top. For a potential that looks like this, we will have a finite or infinite number of discrete eigenvalues and then a continuum above. If that potential is shallow enough, then it may be that there is not a single bound state. We will soon cover the uncertainty principle very closely. I can already tell you when that happens. Imagine that this dip here in the potential is in a very small region and it's shallow. In this case, if a particle was to be localized in that little region, well then delta x is small, delta p is large. Therefore, the energy uncertainty is large, therefore it can escape. So if your particle is to be, if you try to confine it in a potential that has a dip that's too small and too shallow, it will escape and there's not a single bound state. But generally there will be at least a few bound states. And then on top of that, there's going to be a continuous spectrum. Now, one of these potentials you've seen in prior courses of quantum mechanics, of course, and that would be the potential of the harmonic oscillator. There you would have a 1 over x potential, and that looks, of course, like this. And same story as above. What you have is that there is a discrete spectrum, and then the eigenvalues get closer and closer and closer. You have infinitely many eigenvalues, each with a normalizable bound state wave function. But then on top of that, you have the continuous spectrum as well. So the full spectrum of the hydrogen atom consists of a discrete spectrum of bound state corresponding to bound states, but then also the scattering states, which describe electrons that are so energetic that they are not bound by the proton, that they merely scatter off it. Now we are at a special point in our course because we are about to complete the more mathematical parts of the course, and we are about to move on to the physics of quantum mechanics, and building on all the mathematical framework that we've developed already. But before we move on to the physics from next lecture onwards, today let us clarify a few more lingering things that some of you have kept asking me about. So let's just clarify these points. One question that comes up all the time in quantum mechanics is what's behind the Dirac delta? It's not a function. So what is it? Can we somehow put this on a solid mathematical footing? Second, and that's related to it, recall that if we have a discrete basis, let's say some discrete basis that we may call Bn, then we can define an operator p hat to be this, Bn, Bn, the ket-bra Bn, Bn. And then we have that p hat is self-adjoint and p hat squared equal to p hat, and therefore p hat is a so-called projector, which is a very useful thing to know. So this is not the momentum operator here, right? This is meant to be a capital P. And what we did is we defined a projection operator here. Projection operators are very important observables because they are the most elementary observables there are. Because they are observables that carry exactly one bit of information. Projectors, it turns out, have eigenvalues 0 and 1, just like a bit in a computer. So projectors are the observables that correspond to yes/no answers. Is the particle in this interval or is it not? Does it have that energy or does it not? That's one bit of information. So projectors are very important. And there's a problem. We can't do this with operators. We can't do it with vectors that are from the continuous spectrum. You see, there we have that p hat squared equal to p hat. No. Why not? Well, let's calculate it. X, 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 x is what? It's the Dirac delta of 0 at x, x, right? Now that is undefined. So that's an issue. How to deal with that? How to handle? Third point. I've heard some of you complain that one of the exercises was a bit tedious because, well, maybe not only one, but one exercise was a bit tedious because you had to handle integrals and series and combinations of integrals and series. And it's just inconvenient. So how to handle the continuous and the discrete simultaneously in quantum mechanics? How to do series and integrals in a unified way. Now, the answer to all three of these, let me just write here, answer to all of them is the so-called Stiltius integration method. This is what is really behind much of these issues. It's usually not spelled out, but since we are trying to do things here properly, I mean, at least getting to the bottom of things, even if we are not striving to mathematical rigor as in a pure math course, we still try to understand everything in its deepest essence. So what is the Stiltius integration method that apparently answers all of these three questions? The Stiltius integration method is motivated by the following. Remember how integration ordinarily works. We integrate from a to b some function f of x dx, and we do that by taking the limit for epsilon going to 0 of the sum over I, where we sum up rectangles. Xi plus 1 minus xi. Right? So what is this? This is a Riemann sum here. Let's say here this is f, this is x. And here we are dividing up the x-axis into points xi. Oh, I'm sorry, but the software is messing these things up here. What is this? Okay, so this is xi, and this is xi. I don't know why that happens. All right, this is xi plus 1, right? So this is xi plus 1, xi plus 2, etc. And then let us look at this rectangle here. I don't know why this software is producing extra bars here. So in any case, now we pick another point in here. Let's call it the point x bar I. It's an arbitrary point in the interval. And then we look at this rectangle here, right? This rectangle here has a certain area. What is that area? It's this area. It's the height, f of x bar I, times the width of the rectangle, xi plus 1 minus xi. And then we sum all of them up. In this way, we get the area under the curve. We get the integral, right? The usual business of integration. Now, the Stiltius integral is similar, but with a twist. So Stiltius integral. Here we integrate from a to b. And, oh, I should say, first of all, we choose an integrator function. From integrator function m of x. Then the Stiltius integral is defined to be the integral of f of x, and then instead of just writing dx as we did up here, the Stiltius integral writes here dm of x, and defines this to be the limit for epsilon going to 0, and then it's all very similar. Sum over all I, and then we have f of x bar I, so far no change, but now m of xi plus 1 minus m of xi. Okay, why does it help to use an integrator function? Well, let's look at an example. First of all, the simplest example of an integrator function. So, example, we choose for our integrator function m of x that it is simply x. Well then, therefore, recover the ordinary integral. I don't even have to calculate anything here, because you see, if we replace m of x by x, then this becomes literally dx. And also over here, m of xi plus 1 becomes xi plus 1, etc. So it's literally the same. So let's remember this. If the integrator function is simply chosen to be x itself, we obtain the ordinary integral. Now, what do we get when we choose for the integrator function? Example, m of x equal to c, constant. Well then, what happens then? In this case, m of xi plus 1 is the same as m of xi. It's a constant. So therefore, this is always 0. The integral is 0. Therefore, integral vanishes. So whenever we do a Stiltius integral with a constant integrator function, we get 0. If we choose the integrator function to be x, we obtain the ordinary integral. Let's see, what other examples can we do? Let's do the example where the integrator function is a step function. So it's sort of constant, but then it jumps, and then it's constant again. So example, let's say our integrator function is chosen to be the Heavyside function. Remember how that thing looks like? It is 0 if x is smaller 0. It is 1/2 if x is equal 0. And it is 1 if x is larger 0. So the way it looks like is, of course, x, and here's theta, and it comes in from 0, and then it jumps up here, and it goes like that, right? Technically, I shouldn't have drawn that vertical line. Instead, it comes in here, and then at 0, it's the value 1/2, and then from x larger 0, it's that value here. Okay, that's the Heavyside function. Heavyside theta. Now, here's a proposition. And you will see it again in the exercises. Namely, the integral from a to b, well, assume that a is smaller 0 is smaller b. So we are integrating from the left of the origin to the right of the origin. If we did not, if we just integrate on the left side, so if a and b are both negative, well then our integrator function is constant everywhere and the integral is 0. If a and b are both positive, then again the integrator function is constant in our integration interval, and so the integral is 0. But if the integrator function has a step in the integration interval, namely like this, then the proposition is that our Stiltius integral comes out to be f of 0. And in order to work that out, all you have to do is go back to the definition of the Stiltius integral. So here you plug in your function, and here you plug in your Heavyside function. So here you simply have to evaluate the Heavyside function. So you have to discretize your axis and then put in the Heavyside function there, and then you should be getting the result. All right, so that's the proposition. Namely that when we integrate a function f over a Heavyside function as the integrator function with the Stiltius method, then we get the function evaluated at 0. Why is that important? Well, remember, the Dirac delta is defined in such a way that when you integrate from a to b, f of x, delta of x, dx, then you get f of 0. this is significant. We can now identify what the Dirac delta really is in terms of the Stiltius integral. So what is going on here? To see what's going on here, let us look at another example. Assume that m of x is C1, which is to say that it is differentiable and its derivative is continuous. Right? So differentiable, let's assume that our integrator function is differentiable and the derivative is continuous. Then, what do we have? By chain rule, we have that the integral from a to b of f of x with the integrator function dm of x is equal to, well, the integral from a to b, f of x, and then it's dm by dx, or dm of x by dx, dx. You see, if m is a differentiable, then we can do this. And so we obtain this. And in other words, we now see what the Stiltius integral trick really does. The integrator function simply leads, at least when the integrator function is differentiable, continuously differentiable, then the Stiltius integral is simply an ordinary integral, where this is the integrand of an ordinary integral. Integrand of an ordinary integral. And we recover, of course, what we saw earlier, namely if the integrator function m of x is x, well, then we have dx by dx, that's just 1. Okay, so we recovered it. If the integrator function is x, then the Stiltius integral is just the ordinary integral. We also recover that if the integrator function is constant, well, then we have that differentiating the integrator function with respect to x gives us 0. So the integral is 0 everywhere. So all of that is also fine. But we now also see what it means for the relationship between the Dirac delta and the Heavyside function. Namely, we see that via the Stiltius integral, we have that if m is the Heavyside function, right? If m is the Heavyside function, then this is the Dirac delta, right? So what we have is that the Dirac delta is equal to the d by dx of the Heavyside function. This is often quoted in the literature without saying much about it. But that's what puts it on a solid footing. And very importantly, this thing here is an ordinary function. It is not differentiable, all right? Not everywhere differentiable, but it is still an ordinary function, right? It just maps every value of x into some amplitude. This, however, is the critical thing, right? This is what we need the definition for. And what we achieve with the Stiltius integration is that we actually never have to work with the Dirac delta. Stiltius integration allows us to work with the m of x, never having to differentiate the m, never having to work with the Dirac delta. Everything is now expressed in terms of ordinary functions, namely like the Heavyside function here. Remember, just to make that point absolutely clear here, this is the definition of the Stiltius integral. When m is the Heavyside function, then on the right we have Heavyside functions occurring, but we do not have the derivative of the Heavyside function. It's not needed, right? So this makes sense. The left-hand side makes sense, the right-hand side makes sense, even if m is a discontinuous function, such as the Heavyside function. And the result of the integral is that it effectively gives us the action of the Dirac delta. So, so this is defined by the right-hand side. Okay, so whenever we use the Dirac delta now, we know we can always use the Stiltius integral and express everything in terms of the Heavyside function, never having to differentiate the Heavyside function. Now, we can use the Stiltius integral, therefore also to unify series and integrals. Okay, let me give you an example here. We can now unify series and integrals. We don't have to write them separately anymore, because everything is a Stiltius integral now. Sums are Stiltius integrals, series are Stiltius integrals, and ordinary integrals are Stiltius integrals. Here's the example. Here's an example. Choose m of x, our integrator function, to be the sum of several Heavyside theta functions, x minus xi. So it's a step function. M of x is a step function, right? It's constant until one of those Heavyside functions kicks in, and so on, right? So this function looks like this. It goes like this, and so on. Okay, when we have an integrator function like this, then what do we get? What is the integral now, the Stiltius integral? Well, then the Stiltius integral over the real line of f of x d m of x is then equal to, by the same method as above, sum over I f of xi. We're only getting contributions where the steps are. And if you want to spell it out using the Dirac delta, then of course what we get is this. Using delta, what we have is that the integral over r of f of x dm of x is equal to integral over r. And now I'm abusing the notation dm of x by dx. I'm abusing the notation here because m of x is not differentiable, right? M of x is not differentiable because it's the step function. Therefore, we can't do that really. But if we do it nevertheless, if we just symbolically write it this way, then what do we get? We get f of x, and then we get these Dirac deltas here. So we get, and this is the sum over all I, and then it's the delta of x minus xi, because if you differentiate one Heavyside function, you get one Dirac delta. If you differentiate the sum of Heavyside functions, you get the sum of Dirac deltas. And here you have the dx, and this would be ordinary integrals now. And so you get that this is equal to the sum over all I f of xi. But you see, this would be using the shaky notation and terminology that is usually used as a shorthand in quantum mechanics. But remember that this piece, these two equations, are not needed. Using the Stiltius integration definition, we go from here directly there without ever having to differentiate m. We're just working with the Heavyside functions. And this is just a notation that we use for convenience, using the Dirac delta, so that we don't always have to write things under the integral. Now, this is all good and fine, but we had a related question. We have a related question left over, namely how to handle, for example, this thing. We wish it to be a projector, like BN, but it's not a projector, right? Because when we square this thing, then we get that this is Dirac delta of 0 XX. That is not well defined. Let's put a lightning strike into this to indicate that there's something wrong with it. Okay, so how can we get the projector? How to get position projectors? Well, what we can do here is first we proceed relatively naively now in these calculations, and then we put them on a solid footing, bringing in the Stiltius integral machine. So we start like this. Start without Stiltius integration. So we define E hat of F. Oh, well, first of all, let's make the assumption that assume F hat is self-adjoint and the spectrum of F hat is the real line. Now, the spectrum is only required to be continuous for what we do now. It could also be less than the real line. It could just be some interval or a set of intervals. But to keep things simple so that we don't have to keep track of the exact size of the spectrum, let's just assume it's the real line. I will later generalize it again. So we define now, so remember the F hat could be the position operator, for example. So then we define the operator E hat of F to be the integral from -infinity all the way up to some real number F. This is a real number F. And then we have here the F, not F hat, F tilde, F tilde, F tilde, dF tilde. Remember, this expression here is the thing that we want to avoid because it's sick. If we take the square of it, we get something ill-defined. That can't be an operator. So, but let's naively start with this expression here. This is what is called a partial resolution of the identity. It is called a partial resolution of the identity. Why? Well, we recover the identity operator, the identity, as the limit for f to infinity of E hat of f, right? Because if we push that upper integration bound all the way to plus infinity, well, then we get the resolution of the identity in the eigenbases of f hat. So by integrating not all of the eigenvectors here, but just some of them, we get a partial resolution of the identity. Now, one can show, you will find that in the exercises, one can show that E hat of f is self-adjoint and E hat of f is E hat of f. So E hat of f is a projector. That is very, very nice. This thing is not thick. The integral E hat of f, remember it is an integral, right? It's this thing. This is nice. This is not thick. This is going to play the role of the Heavyside function earlier. Heavyside function is not a distribution. It's a regular function. Similarly here, the E hat of f is a projector. It's a very nice thing. By the way, what's the physics of E hat of f? Imagine that f is the position operator. Then what is a partial resolution of the identity? Well, it's the integration all the way up from minus infinity to some location x of the xx projectors. So the E hat of x is the projector that describes an observable with two possible outcomes, namely the particle is, let's say the electron, is somewhere from minus infinity to x, or it's not, meaning that it has to be somewhere from x to plus infinity. That's the observable of a partial resolution of the identity. So let's keep in mind the E hat of f is fine. It's a projector. It's a projector valued function, right, of f. Now recall or notice that if we differentiate E hat of f with respect to f, then what do we get? Remember, E hat of f is the integral all the way up to f of this. Well, by the fundamental theorem of calculus, this is going to be f. So this is equal to f. The thing that's so problematic, because it's not a projector. When we square it, we get something ill-defined. Now, let's see. We want to make all of this now fine, so that we never really have to refer to those guys anymore. Just like the Dirac delta is useful, but we would like to know that we don't actually need it. We can express everything in terms of the well-defined function, the Heavyside function. Similarly, those FF are thick, but it's just a very useful trick to work with them as if they existed. But in the background, it's important to know how to actually make sense of them. Just like we can make sense of the Dirac delta using the Heavyside function. So now, let's write down the full resolution of the identity as the integral over R of f, as we usually naively do. And using what we just had here, this derivative, we see that we can write this as the integral over R of d E hat of f by df, right? I'm just substituting here this expression in here. And now we can interpret this as a Stiltius integral. interpret as a Stiltius integral to obtain, well, what do we obtain? We obtain then that this is the integral over R of, well, dE hat of f. This is the integrator function. This is what corresponds to our m of x before, the integrator function. And here we have no function to be integrated, right? So we just have one, if you like. So this is the integrand. So what have you achieved now? We have now been able to express a resolution of the identity using the F eigenbases, but expressing the resolution of the identity using this family of projectors, this projector valued function E hat of F. And because it is a Stiltius integral, we never need to differentiate the E hat. We never need to actually deal with those guys. Right? This is what we have achieved with that. We have put it on a solid footing, this resolution of the identity in terms of a basis that's consisting of non-normalizable vectors. Now we don't need to worry about those non-normalizable vectors anymore. We don't need them individually anymore. We only need the integrated version of them. And we can consider those projection valued functions to be primary. And then the derivative is a secondary thing. This is just a symbolic notation. This is just like saying that when you differentiate the Heavyside function and you get the Dirac delta. Now we have that you differentiate this projector valued function, you get one of these guys. And similarly, we can express not only the resolution of the identity, but we also get, similarly, we now get that a self-adjoint operator with a continuous spectrum, such as a position operator or momentum operator, or a Hamiltonian of a free particle or something like that, we can always write it as the integral over R, and then F, and then that's our integrand now, and then the integrator function, which is dE of F. And with this, we have arrived at a unified description of self-adjoint operators that can have a continuous spectrum, or a discrete spectrum, or a mixed spectrum. Because remember that when the integrator function is linearly rising, then we have, so if m of x is x, then we just have ordinary integration. That would be like dealing with the continuous spectrum. If the integrator function has steps in it, then the integral actually consists of a sum of terms. And in general, the integrator function may have steps at some places, may be constant in some places, may be rising in some places. The integrator function could be anything. And in the same way that therefore choosing an integrator function in a Stiltius integral gives you a combination of, allows you to write down combinations of ordinary integrals and sums and series. Here too, you can express your operators and your resolutions of the identity with normalizable, non-normalizable eigenvectors, approximate eigenvalues and true eigenvalues, all in one go, just with this formula. So let's just write here, notice this equation, equation star, also works for f hat with discrete with discrete and mixed spectra. And nothing changes. This formula stays exactly the same. All of the non-triviality of the spectrum, the discrete parts of it, the continuous part of it, and so on, are hidden under the hood in the integrator function, which in our case is E hat of F. So if you look up the functional analysis of quantum mechanics, or just functional analysis of operators in general, you will find that the Stiltius integral is the thing to do if you want to describe, for example, the spectral theorem in a more elegant fashion that we have done previously in the course. Okay, now in practice, we do not use the Stiltius integral. We are not much concerned with the Stiltius integral in quantum mechanical calculations. Instead, we just write down things like, you know, x, and use it as if it was no problem. And we also write down things like delta of x minus x naught, and don't worry much about it, that it's not really a function. But I hope to have conveyed now that these things are actually on a solid mathematical footing, namely if they occur inside an integral, because then they can be interpreted as arising from a Stiltius integral, where you don't need to worry about a delta because it's replaced by Heavyside functions. And you don't need to worry about this thing being ill-defined because it's replaced by the integrator function, which is a projector-valued function, which is kind of the integral of this. Okay, so with this, we are closing the chapter, the part of the course that is concerned with representation theory and the functional analysis of quantum mechanics. I will occasionally appeal a little bit to what we learned here, but from now on, it's going to be heavy physics, uncertainty principles, time evolution, and then interaction of quantum systems. How can we understand how a measurement takes place? And what is the wave function collapse? And we will see that the wave function collapse is not mysterious at all. We can actually calculate the dynamics of the wave function collapse. We can literally see how the wave function collapses. And we do that by describing not only the system quantum mechanically and the measurement apparatus classically, but we will describe the system and the measurement apparatus both quantum mechanically, so that the interaction between the system and the measurement device is just part of quantum mechanical evolution. In this way, we will understand how the measurement process itself unfolds. Okay, so we will continue with uncertainty principles next. This is as far as we get today.